Okay, good. Well, I welcome you back to another couple of hours of discussion of the detectors and their raw data. The first thing that I'd like to do, I want to show you now a bit the real layout and hardware. We'll start with a virtual tour of the instrument. I'm hoping that video works well over Zoom. I have a couple of video clips and sound clips to play in this pair of lectures, so let's hope this works well. And let's see, here we are, we're zooming over the Hanford site, and shortly we'll move over into CAD-CAM space. And now we'll zoom down into the corner building where the beam splitter and some of the central optics are, rip off the roof, look at the vacuum system, which contains all of these components and which carries the laser beam without fluctuations over the kilometer distance. We start by imagining the laser coming in from a window on the left through a couple of steering optics and then into a triangular cavity, Fabry-Perot cavity. This cavity serves as a mode filter and as a frequency reference. The beam then goes through a couple of focusing mirrors to bring the beam from its small kind of laser beam, typical laser beam size, up to sort of 10 centimeters, which matches the long arms. It now comes into the Michelson interferometer, hits the beam splitter, and it's split into two. And now we'll go down the 4 kilometer length. Now, the person who did the animation thought that this was the appropriate time to imagine that we see the beam bouncing back and forth between the two mirrors of the Fabry-Perot cavity, and the intensity increasing to about 450 times the input power due to the resonance condition established in that Fabry-Perot cavity. Now let's follow one of those photons down to the end station, where we'll see the end station mirror and its suspension inside its vacuum tank. This mirror, we'll see more of it later on, is suspended by a couple of few silica fibers to isolate it well from the outside world. The beam hits it, a gravitational wave passes, and there could be a change in the path length. We come back down to the place where the two beams recombine from the two arms. In fact, we choose a path length difference so that the beam intensity is at a minimum, but the animator chose to make something that would be easy to see, so it's still a nice bright beam. It goes through, again, a few coupling focusing optics, now into a bow tie 4 mirror cavity and onto photodiodes. Now we have the imaginary gravitational wave that comes along. This would be a very strong gravitational wave, which makes a differential arm length change. This then leads via the Michelson interferometer to a change in intensity corresponding to the length change. And were it to be, for instance, the first gravitational wave we ever saw, we see first instrument noise, and then eventually the signal becomes large enough to be seen in the time trace. So that gives you a quick overview of the system. Now let's start looking at some of the details. This is the laser room, contributed to us actually by Max Planck from Hanover, and it requires extraordinary cleanliness, even though it's in the air, and to avoid burn spots and blown up mirrors and so forth. And so people have to be very clean, and of course have to protect themselves against the laser light as well. So I think they look like extraterrestrials. The demands are quite strong. This particular laser could put out 200 watts, and it needs to be single frequency, single mode. It needs to have very small frequency fluctuations and very small intensity fluctuations so that there aren't cross couplings that mask gravitational wave signals. Here are the vacuum chambers in which the components all sit. And to give you a sense of scale, I invited Albert Einstein to come and give a short violin concert next to the vacuum chambers. The cranes for moving things around and so forth. It's a great big huge hall. The acoustics of it are just wonderful. This is one of the test mass mirror substrates. This is when it was still being prepared for coating. The Ripley surface is in fact a polymer coating that's put on it to protect it. And then this is what that mirror looks like once it's been coated. That yellowish color is a very high reflectivity coating for 1 micron. It's actually fairly transmissive in visible light. And the the engineer there is holding a light to it to look for any defects and also make a pretty picture. This person clearly is inside the vacuum chamber to give you a sense of scale. Let me say a little bit more about in detail. It's 35 centimeters in diameter. It's 40 kilograms. That would be very hard to lift as an individual person. We use little cranes with suction cups, in fact. It's made of ultra high purity fused silica, glass basically. It has very challenging requirements. The surface figure needs to be correct, about lambda over 1000. That's about a nanometer over some tens of centimeters. Less than 1 part per million of the light that falls on it is allowed to actually heat that surface, and the rest has to be reflected. Most all of it's reflected along the beam direction, but about 10 parts per million is scattered out of the main beam. And it has to have a very high coating uniformity because it's one of the measures of flatness of the mirror. Here we see an assembly at one of the end mirrors. Our actual optic is here, and the 4 kilometers is off in this direction. This is a optic which is behind the main mirror. We'll see that in more detail. And this is some kind of a relay system to use some extra light, some green light actually, to help us get the initial system in lock. And again, we put a couple of humans in there to show you how big it is, and we're very careful to remove them before we actually pump down the vacuum system. Here's another look at that optic suspension. Here is that 40 kilogram optic. It's suspended from another 40 kilogram optic via fused quartz fibers. This is part of our scheme to keep the thermal noise as low as possible by making the system as low mechanical loss as possible. Behind it is a mirror chain, which is used to give a very quiet place from which we can push. Let's take a look at the actuator arrangement actually. This is all LIGO's design. Virgo's got a somewhat different arrangement, but here we have a number of magnets and coils which can exert forces against outside shells or between the 2 shells to adjust the relative position of these various different masses in the 4 chains of the 4-level chain of suspensions of pendulums. In the very bottom here, we use electrostatic forces. I'm not exactly sure what this symbol is supposed to mean. I borrowed this slide from somebody, but we put a kilovolt between these 2 objects, a couple of millimeters apart, and then adjust that kilovolt as a way of adjusting the force on this final object to have as little impact on it as possible. Here is a photograph of an actual suspension hung from its seismic isolator in the vacuum chamber. There's a protective cover over the optic here, which is that strange looking thin thing. Here's a CAD/CAM version of the same thing, but I think actually the actual photograph is pretty clear and unambiguous about the way that it's laid out and the way it's installed in the chamber. So the other thing we have to do is to keep seismic noise out. It's not fundamental physics to make a good seismic isolator, but it certainly is fundamental to success. We do this to avoid the masking of gravitational waves. So we have to keep the seismic noise well outside of the range of frequencies where we want to be able to detect gravitational waves. This, by the way, is a progress we made in LIGO between our initial LIGO version and the advanced LIGO version in this frequency domain. But we also have to enable practical control systems. We need to be able to push on all of those mirrors. We have to be able to do repositioning for tidal forces and so forth and so on. And so advanced LIGO uses an active servo-controlled platform and then multiple pendulums as the final stages of isolation. There are 3 layers, each one of 6 degrees of freedom. This is an external support pier, which is on the ground. There's a hydraulic system here that senses all 3 translations and all 3 rotations around those axes and provides feedback to reduce that to a minimum. It continues up at a higher level. I think we've got a more detailed view of that. Yes, here we are. So this is that suspension system with 4 layers of pendulum, which acts as a passive isolation system. And then around that, we wrap this system of 6 degrees of freedom, 6 degrees of freedom, and 6 degrees of freedom. Each one with sets of very low noise seismometers to bring the noise motion in inertial space of this platform to a minimum. There are also sensors outside on the ground. And this is what it looks like as a CAD/CAM version with these kind of 2.5 or 3 meter tall piers supporting the mass through a set of bellows and bars that go through the vacuum system and then into the vacuum system. It's very hard to explain how this is all folded together, this 2-layer inside seismic isolation platform. One can make out the trapezoidal vertical springs for one of the stages. Then there's a short pendulum which hangs the next stage down. This is the next stage down, so forth and so on. It's carefully folded to be compact. I should mention also that these plates are all machined to micron flatness. It's an incredibly high precision device. Now I want to show you another film clip, and this time there's some sound. This is what it really looks like inside the control room of a LIGO interferometer, and it gives you a sense of the number of parameters that are monitored by the operators and just a sense of what the space is like. It's a handheld camera, so it's kind of jittery. You can see the spectrum of the performance at the moment that this was taken. There are a whole bunch of other diagnostics that are shown here. There's pressure in the system. There are measurements of non-stationarity. There are degrees of freedom. There are the stages of locking. There are various astrophysical measures. This is the site monitor. Here are some screens that show the intensities of the beam spots. You can actually see some of the dust spots that are lit up there. We take a little bit closer look at some of the measures of stationarity of the noise and the astrophysical distance to which one can see. Let me ask, was it possible to hear the sound from that clip? Could someone speak up and say?
Yes.
Okay, great. So now I've given you a pretty deep introduction to the instrument. Let me talk a little bit about how we get from electronic signals to something that's usable for analysis. Which will be treated, the analysis will be treated by others later on, but I want to give you a little bit more of the sense. One very important thing is calibration. General relativity makes predictions for the luminosity of coalescing binaries. The signal of the detector depends on the distance 1/r. I'll note that it's not 1/r squared. We look at the amplitude of the wave, not like most electromagnetic detectors that look at the power that's received. And there's also some degeneracy with the inclination of orbit, but still you get extremely useful information by knowing what the real quantified strain is. So we can, and with that information, we can, for instance, get a measure of distance from the source to the Earth. And in that way, you can, for instance, find an alternative handle on the Hubble constant. But it requires an absolute calibration of the detector in strain. The technique that LIGO uses is to shine a laser on the test mass. This is a different laser entirely. We monitor the intensity of that. We modulate the intensity of this beam, which modulates the momentum transferred from the photons to the test mass. This is, again, of course, it's a random string of photons. You have to be sure that you're not introducing additional noise to the measurement by throwing these photons at the test mass. That can be arranged. But this pressure then is just directly proportional to the light intensity. And so the motion of the test mass can be calculated with some great accuracy if you know things like the angle of incidence of the beam, the mass of the object, its moment of inertia, and then the power that's actually falling on the detector. This is another schematic diagram of what it looks like. We apply the forces in a balanced fashion at the top and the bottom of the masses. To make sure that we don't introduce tilts in the mirror. We can adjust the relative intensities of the two to balance out that torque that would be otherwise exerted. Of course, it needs to be centered left-right, not to give torques, rotation torques. The accuracy that one can obtain with this system is about 5% and about 3 degrees over the range of frequencies. Much more information is actually available for the exact uncertainties at each one of the frequencies to aid in doing a proper job of parameter estimation. It may be possible to improve this approach by about a factor of 2, but it's interesting, the uncertainty in the world standards for the measurement of laser light intensity is a real limit to how well we can calibrate the gravitational wave detectors. And there's even been some serious discussion, if we get to the point of having high enough signal to noise measurements of astrophysical sources, we may actually use that to calibrate the light intensity monitors for measuring light intensity in all places on the Earth. It's a crazy idea, but light intensity is a hard thing to measure accurately. There's a secondary system in development. It was first gotten going in the Virgo collaboration, but now everybody's trying to make one to effectively make a dynamic Cavendish experiment. What you do is to put a couple of masses and swing them around a central pivot point in the vicinity of the mirror. And then what we would traditionally call gravitational attraction, of course, it's just deformation of space-time, but the gravitational attraction then causes the mirror to move in a way that can be rather well calculated. You do have to be careful that there's no cross-coupling from mechanical, magnetic, electrostatics, electronics, that sort of thing. But this is an alternative secondary way of doing calibration, could be carried from detector to detector, and may actually ultimately lead to higher precisions. But the bottom line, though, is the ability of detectors to give an independent measure of distance, not based on supernova luminosity or something like that, is extremely nice, and this calibration is central to the value of gravitational wave data. Well, I want to talk about a little of the data quality that comes out of the instrument. And the first thing I'm going to do is to deliver on my homework assignment from yesterday. There were some questions about what the narrow spectral features were in LIGO spectra. I won't dwell on this too much, but I wanted to just walk through some of the features. First off, I want to say I've exclusively focused on binary inspirals in my presentation. There are many real examples of detections now. It has the virtue of being these calibrated standard sirens. It exercises the full bandwidth of the instrument. But of course, there are a whole range of other astrophysical targets that are being sought: stochastic background, supernova, cosmic strings, and spinning neutron stars with asymmetries. The signature of this latter source is a narrow spectral feature. In fact, it's not fixed in frequency, even though at the source, the frequency is extraordinarily well fixed. It's shifted around by the Doppler shift of the motion of the Earth with respect to the source, which complicates the analysis. I won't talk more about that. Somebody else will, I hope. The instrument's own spectral features need to be known very well to reject imposters for this particular signal source. And we also want to minimize the number of these instrumental lines because you can't detect easily directly on that frequency where there is a contribution from the instrument. This is a high resolution Fourier transform of a signal, of a data packet in the range from 20 hertz to 100 hertz, the usual logarithmic vertical scale. And each one of these things labeled with a lollipop with a candy on a stick is a spectral line. You should be horrified at this. This is a listing of all of the different spacings. This sort of behavior at low frequencies makes it much, much harder to find quiet spaces to do these continuous wave observations. If we zoom into a couple of these that are actually in a quieter interferometer, that interferometer has now since mostly been quieted down happily. But here are a couple of the details that one can see when one looks at the full spectrum and we look at the largest peaks. There are a set of peaks that are in the hundreds of hertz, which are due to the beam splitter violin modes. Again, these are the suspension fibers where a half wavelength fits on it, or a full wavelength, or 3 halves, and so forth. A whole harmonic series excited by the KT of energy in each one of those modes makes this set of frequencies here. And there are a variety of different frequencies because there are 4 fibers that suspend the beam splitter. They're slightly different in diameter, slightly different mass linear density, gives different frequencies for the strings. They can also be under slightly different tensions. We have calibration injections. We have continuous excitation by that photon calibrator that show up in very nicely well-defined lines. The suspension fibers for the test masses form a forest. There are 4 suspensions. Each one has 4 fibers, so that's 16 lines. And again, we have some distribution of lines over a narrow frequency band, which correspond to the different tensions and diameters. There are also some more calibration lines down at low frequency. There are some modes of the optics that roll around their axis that has a cross coupling to the optical path. This is the 60 hertz that is everywhere in the US, like the 50 hertz in Europe. Beam splitter suspension, 2nd and 3rd harmonics, up 600 hertz, 900 hertz. And just to note, I was looking at my email this morning and looking at the logs from the laboratory. Someone has observed another set of comb frequencies which need to be pursued. A 2 Hertz comb with a 0.97139 Hertz offset. Harmonics 23 to 26 are visible. This is a hunting operation to chase down the source of each one of those things. So now back to the foreseen slide deck. As I say, the noise, the signal from the output of the interferometer is rather imperfect, and you've seen one nature of that. Now let's look at some more transient measures. What I'm going to show you here is a little animation. This is a time series at the output of the gravitational wave detector. This is not a gravitational wave signal. This is a defect in the data. And we'll be watching simultaneously down here the frequency spectrum of the transform of short Fourier transforms of this noise to show how it is disturbed when we run over that noise. Here we come. It's going to bounce up the intensity of the in the transform here on the bottom and would mask a passing gravitational wave at that time. Here is another way of looking at that same event. Again, the time series up here. If you just take a standard spectrogram, which would be a time series, Fourier transforms of the time series, and we layer them in a color map along time axis, this is what you would get. We actually prefer to look at other slightly better transforms, a Q transform, where you change the, you do a fit of the data in another orthogonal set that involves a series of functions which have different Qs at higher and higher frequencies. That can bring out the nature of the scattering somewhat better and make it easier to track down what the source is. Here are some other examples of data defects. There's a thing which are called blip glitches. These are actually delta functions coming out of the measurement system. This is the biggest contributor to the transient gravitational wave search backgrounds. It's seen in both LIGO detectors, also the Virgo detector. They are non-coincident. It's very good to have multiple detectors so that you can reject these as being not gravitational waves. But we have not yet been able to find the correlation with any instrument behavior or environment, or to change their frequency notably. That's ongoing work. There's also non-stationary noise, say up in the 600 to 200 Hertz region. This is probably a scattered light phenomenon, light falling on a reflection and the vacuum chamber moving with respect to the stationary mirror and causing a modulation of the path length, but still to be addressed. Here's another case of, here's another hint of how we go about chasing these things down. We have many, many sensors distributed throughout the detector. And one of them, we have some, I don't know, some dozens of microphones. And what I'm going to do is play for you a clip where we will hear the sound recorded in this microphone at the end station, and we'll watch also the strain at the same time point. And I'll get this going because there's actually 30 seconds of just the background sound of being in the end station of the LIGO interferometer. What you're hearing there are a whine, high frequency whine from fans that are cooling computers, and then the lower frequency are larger ventilation systems that are circulating clean air. And once we've gotten 30 seconds into this clip, you'll start to hear a deviation from this fairly constant background sound. There it is. And you see it appearing in the microphone end station spectrogram, and also appearing through some kind of cross-coupling from acoustic pressure into the gravitational wave strain. This was one that folks were able to track down, and it has a fun story. This is a photograph of that end station building. We use liquid nitrogen. It was at a fun moment. We were just installing
David?
one of our tests. Yes?
Sorry to interrupt. I didn't hear, I heard almost anything what you said with the noise. Could you briefly summarize?
Yes, of course. I'm sorry. I don't know what the balance is, of course, between my voice and the sound that comes from these clips. I'll be careful not to talk over them in the future. So what the micro, no apologies. The microphone sound that we heard, the sound we heard was from a microphone that was sitting in this building. And at the bottom, we saw the time spectrogram of that, not as an animation, but as a snapshot. and there was about 30 seconds of time during which we heard just the quiet hum of computer fans and heating, ventilation, and air conditioning systems that were running. Then after about 30 seconds, we heard bunk, 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 bunk. And we saw that both in the spectrogram of the microphone in the bottom frame and in the gravitational wave strain at the top. And that gives you, first off, a notion of one of the ways that we try to track down where noise sources are by having a set of distributed sensors throughout the environment. And then also gives you a notion that there can be cross-coupling from the acoustic environment around the interferometer to the interferometer, despite all that we do to try to insulate it with vacuum systems and insulators and isolators and so forth and so on, there's still some coupling. So it was possible to trace down where that came from. We have liquid nitrogen tanks here, which are used for a vacuum cold trap. And then there's a tube from that liquid nitrogen tank into the body of the building, which is shown in a close-up here, or even more of a close-up here. One of those pipes is rather cold because it's carrying in the liquid nitrogen. And it was noted by the researchers who were trying to track this down that there were scrape marks on that ice. They set up a camera to catch anything that might happen in that region. And they discovered that ravens perched there and drink the water that comes, can be melted from this ice. To test whether or not this hypothesis was correct, we made up a mock raven and introduced some excitation of the tube with a hammer and discovered that that signature matched very well the in amplitude and in frequency characteristic what we had seen. So this is the kind of sleuthing that needs to be done to reduce transient noise sources in LIGO. I have another example where, let me give you an introduction, then I won't talk. Here we're going to hear a microphone that's sitting in that place where I was, the very, very clean laser room, the photograph I showed you with the folks dressed in white with goggles. And we'll hear that microphone and we'll see what's causing these spectrogram peaks. And that also showed up in the output, the strain of and the function of time, and due to a cross coupling between the laser acoustic environment and the detector. So let me play this clip. This is the background, is mostly 60 cycle hum. I think you can imagine what that noise source was. We have telephones here and there inside the vacuum, inside the large chamber there where all the stuff is. All those phones are supposed to be turned off when people leave the room. It was forgotten to turn off here. So this was an easy one to trace down. So this physical environmental monitor that's giving us these data, there are sensors distributed throughout the observatories, sensing all known and suspected coupling from the environment to the acquired signal. And then each one of those sensors, those external sensors, is intended to have a sensitivity greater than the detector to each of the measured parameters. This sounds kind of challenging, but then you think about it, we try to reduce the sensitivity to acoustic noise as much as we possibly can. And then we put a very low noise microphone in that space. Well, in fact, it's not so hard to get a microphone that's lower in noise than the noise level of coupling from acoustics into the system. And we have a range of other detectors like that. We then measure transfer functions. They could be true transfer functions that measure both phase and amplitude, or in the case that there's a wandering coupling coefficient between the external influence and the inside, we have to resort to just looking at the ratio of power for signals from the outside into the inside. And so that gives us a number that we can use to multiply the quiescent, the quiet background case, so that we can determine what the coupling should be from that external noise source to the interferometer. We always look, whenever we have an event, we immediately look at all of the auxiliary sensors at the time of that event as a way of helping to ensure that we're not being fooled. And for the fun of it, I laid out here the range of sensors involved: 47 accelerometers, 18 microphones, 11 in-building magnetometers, 6 in-building seismometers, 5 RF antennas and receivers, 5 weather stations, 3 tilt meters, 2 high-sensitivity volt magnetometers, 2 high-sensitivity volt seismometers, 1 cosmic ray detector, power voltmeters and amperage monitors, interior and exterior video cameras, and 1 turtle dove in a pear tree. So what's the impact of this work? On the left side here, I show you a histogram of the rate of things that look impulsive versus their amplitude in a logarithmic measure of signal to noise ratio. And so what we see here is that before the work is done to remove the background, this is the histogram of those false alarms that can mask gravitational wave signals with a tail up here at high end. After all of the bad data, some tiny fraction of it, some 10% or something of the data, are removed by identification of defective times, the statistics improve remarkably, and in fact allow us to start uncovering signals at this sort of SNR. They would be completely hidden were we not to make this sort of work. We move from, in the case of this particular signal, a false alarm rate of 1 in 320 years for the raw data to 1 in 200,000 years with the data quality information applied. So it's worthwhile effort, but it's hard work, and it requires people who can really just crawl all over the apparatus and spend extended periods of time making these characterizations, looking for defects, playing rock and roll in the large system and looking at what frequencies it couples most effectively into the interferometer, and then looking for the scattered light path that's being excited by that rock and roll, that sort of stuff. I think it's a lot of fun. So now let me move out another layer and talk about gravitational wave detector networks. It's sort of a meta instrument topic, because you can't hear when this thing is going on. Let me tell you what I want you to do with this. This is the kind of thing which you may have heard in the past if you've paid attention to press conferences when we've made discoveries. What you will hear is the actual strain as a function of time output of the photodetector, suitably filtered and then put into the audio system. And you'll see the spectrogram from the Livingston detector on the top. I think it's Livingston, Hanford, and then Virgo. It could be in the other order. And usually when I play this, I say, so don't pay too much attention to the noise you're going to hear. Try and hear the sound of the binary in spiral as it causes the path length between our test masses to wiggle. But this time I want you to forget about the binary neutron star and listen to the sound. This is what the sound of the output system looks like. But I'm going to also call your attention to another thing once the clip is finished. Here we go. Let's see if I know how to start this up again. I'm going to back up actually and move into it. So you probably, in fact, did hear the sound of the binary in spiral there. But that's what the noise looks like. But there's another thing I want you to notice. The trace is visible in the Hanford and Livingston instruments, but not in the Virgo instrument. And I assure you, it's not because the Virgo instrument wasn't sufficiently sensitive to detect it. Let me talk about the antenna pattern for a single gravitational wave detector, interferometric detector. This is a sketch of the vertex and the 2 long arms, and the distance from this vertex point to this surface is proportional to the sensitivity of the instrument to waves along that axis. It's called an antenna pattern. So we can see it's most sensitive perpendicular to the plane of the instrument, and that makes sense. You can maximally excite the differential motion of the 2 arms if you come in from above, or equally well from below. Can't distinguish between those 2. If you come in along one of the tubes here, you can excite motions perpendicular, but it's all of the forces exerted, if you want to speak of them that way, by the passing gravitational wave are perpendicular to the direction of propagation, and so there's no excitation of this arm. So the sensitivity is down to 1/2 at the side points here. If you happen to come in at 45 degrees, the forces of the wave are all perpendicular to the optical paths, and you actually have a 0 at this point in response for a beam that's exactly targeted at the right position. So what's good about this? The detector sees almost the entire sky with good sensitivity. What's bad about it? A single detector only gives very limited information on the source direction. And so you need to do something to improve that. The solution is to use multiple detectors working together to perform triangulation. I think the other thing I want to note here, coming back to my comment that the signal was not visible in Virgo, that source fell on Virgo very close to 45 degrees. The Virgo data were critical for localization because we knew its sensitivity and its noise level. Knowing that there was little signal there gave particularly interesting information about the orientation of the source. I think it's a really cute illustration of how the antenna pattern, even if it's sort of not at all like that of a telescope traditionally, can still give very good information. LIGO and Virgo are similar instruments in concept, differences in details. I've mentioned some of them as we've gone along. Virgo has 3-kilometer arms. LIGO's got 4-kilometer arms, and there are 2 detectors in the LIGO pair. These are separated by about 3,000 kilometers. I don't actually know the distance to Virgo. It's probably more like 10 or 15,000 kilometers. The instruments observe together, share data in real time, and perform position identification together. The collaborations share all data, all analysis tasks, and all the publications about astrophysical observations. It's a win-win-win since there are 3 detectors, but since there are 13, 14, 1,500 people involved, I'd have to say win many, many times to cover all of the ways in which this is advantageous. With that 3-detector network, we can do this process of triangulation. I think the specialists don't like to use that terminology because there are other aspects besides just the timing which are used to obtain the best estimate for the position of the source. But here's another little animation for GW170817. I think it first actually hit Virgo and then Louisiana and then Hanford. And by knowing the time of arrival, it was possible to give a good estimate for the distance to the source, or I'm sorry, the position of the source. And by having 3 calibrated detectors, we could give a good estimate for the distance to the source.
Sorry, David,
after having done, yes.
There are a couple of questions. One is, then does the polarization observation help to localize the source direction?
I think this is getting outside of my area of expertise. I think not so much. That's an additional orthogonal piece of information to which you need to fit. And if anything, I could imagine that having that extra degree of freedom decreases the confidence in the net result. The 3 detectors are just enough to resolve the polarization after you determine the position. If we had more detectors, then I think that, I'm improvising on the spot. I'm not really sure. How's that? Ask Neil Cornish when he gives his talk on data analysis. He'll be able to give you a proper answer.
And Luis, do you want to ask the question?
Yes. Do you have any estimate on how the percentage of the sky that we are not covering because of these holes, and if there is any overlap between these spots of low detections between the 3 detectors?
I have a good slide for that coming up.
Okay, I will wait for that.
Let's give that a try.
Okay.
And so I want to show here, just for the fun of it, here is some kind of projection on a sphere of our uncertainty of the GW170817, the same event. If we use just the LIGO detectors, we have an uncertainty which is sort of banana shaped. And I think there's actually maybe an echo on the other side of the sphere. I don't think so, perhaps. But at any rate, you can see that there's a very large uncertainty region if we have just 2 detectors. But when you add the 3rd detector, Virgo detector, which happened to happen in the temporal sequence due to some data transfer delays. Suddenly the precision goes way up. Similarly, you can get a very good estimate for the distance to the source as you add more detectors. So what enabled the remarkable achievements in this new field? Collaboration. I think it's extremely important that you come away from this set of talks understanding this critical aspect of how we got through this process. We started out with some tabletop scientists doing precision measurement. Frequently people who are specializing in laser research or in atomic molecular, that sort of stuff. There's the tradition of this team was in very small groups, small projects, and often with some pretty severe competition between groups. We were joined by general relativists, theorists, astrophysicists, but they very much had the same tradition of working independently, striving to publish first, that sort of thing. There was a real transformation when high energy physics got involved. So people came in particular in leadership, but also throughout the organizations in both LIGO and Virgo, people who are used to working in large collaborations, used to trying to engineer large projects, knew about project organization, computing, and the analysis process. The funding agencies also saw a need for a shift. These kinds of operations were being funded with hundreds of thousands of euros per year or something like that. The kind of demands that we were placing on funding agencies was more like hundreds of millions of dollars. And there's a real skill in spending appropriately that kind of money. It's not the kind of thing that somebody can do after having built an atomic trap. The goal pre-discovery was crystal clear to make an initial detection. And this allowed the collaborations to focus very carefully on that goal. After the collaborations were formed and stable, we started to form meta collaborations. Now we're at the LVK, the LIGO, Virgo, CAGRA scientific collaborations, all sharing data, still remaining independent collaborations. The science that's possible in this larger meta collaboration is qualitatively greater. I think the position localization is a good example of that. And the sociology of a mostly non-competitive funding environment it can be nurturing and quite supportive in a way that small independent groups and the competitive spirit that comes out of it can not be. Lisa and the space-based detector, I'll talk more about that, pulsar timing as well, also are in collaborations and consortia and enjoying the ability of the synergy that comes from having many people working together on a common goal. And there's probably about 3,000 persons now who are really deeply engaged in the development of new detectors and the exploitation of the data from them. This is a really important part of actually succeeding in this. What does the future hold? I think we could afford to take at this point a 12-minute break. And maybe first there'll be, if there are any questions, I'm happy to field them. But otherwise, I suspect that we should do well by taking a break until the top of the hour, which is by my clock 12 minutes away. And then we'll be able to wrap up. So are there any questions for me?
Yes, first of all, someone, Yasang Yu asked whether you can tell us more about the polarization calibration.
Polarization calibration. I'll give you a superficial answer. The polarization calibration, the precision with which we can see the polarization of the source, is dependent upon the amplitude and phase calibration that I talked about. And then also, of course, the signal to noise ratio with which one sees the source. I don't know what the mapping is from the amplitude and phase calibration of an individual detector to the precision with which a polarization could be resolved for a given signal to noise ratio. I'd either have to take that as homework, or what I'll actually do is pass the question to Neil Cornish and see if he can give you a proper answer for that during his lectures.
So there is a question by Alexandra. Maybe you can ask it.
Sure. Well, first, thank you very much, David, for the very nice lecture. I was just wondering, because you mentioned some competition, and so do you mean competition within the LIGO collaboration itself, or that there were different groups trying to work on some interferometer?
It happened in a couple of different layers. I mean, initially, as I said, most of the people who started to get excited about building interferometric gravitational wave detectors had been doing something beforehand, looking at atomic clocks or doing some kind of precision time measurement or doing some kind of precision, some sort of precision measurement or so. Those groups had some friendly competition and some communication at meetings and so. When the field got started with LIGO, Virgo, there were also groups in Germany who continued on to build a smaller machine, but those groups were very much in the same mold of having most of the communication between the groups taking place at scientific meetings where ideas were shared, triumphs reported, questions posed, and then the groups tended to work somewhat independently and somewhat in competition. It was a gradual transition from that state to the one where people realized that the compromises that are required for collaboration would be worth it in the long run. And it was not an easy transition. And there are some people who decided that they would rather work in smaller groups and on some other project than to continue in the field, rather than give up the sense of independence and to give up the short author lists papers. But then many people decided to stay with it. And of course, many more have joined in the meantime. So there's a sort of an adiabatic transition. It wasn't adiabatic. There was a transition which had a couple of step functions, which were rather hard, but which led to the situation that we're in now. And because you asked the question, I'll say actually, if I were to make a plot of competition versus time, I would say that the competition started out rather high, came to a real minimum around the time up until we made our first detection. It's starting to increase again. The additional visibility to the world of our science, the lucrative positions, which are now wonderfully available for scientists who've been working in this field, leads once again to people trying to show how their individual contribution was particularly important to this or that discovery. I'm not making a criticism of that. It's part of a very natural evolution of the field. But still, there's a great deal of activity, which is very highly collaborative, and it still is a very wonderful place to work in that sense.
Okay, I see. Yeah. Thank you very much.
So Marta has a question about the control room.
Yes.
So the noise that we heard was quite deafening. So I was wondering if it's the actual level, or you have highlighted it.
I had no control over the level of sound in that clip. It's not that loud. I don't know how loud, of course, it was in your headphones or loudspeakers anyway, but it's not that loud. It's not like being in a computer server room. There's one of those just right next door to that spot. It's like being in a room full of desktops or of workstations. So, there's a bit of a hum from some fans. There's a printer that comes up from time to time. Often on loudspeakers, there is the signal of the interferometer being played in real time. It's an extremely useful diagnostic for the people who are keeping track of the operating condition of the instrument, to be able to hear what kinds of sounds are coming out of it. And that was not in operation for that clip. The sound that we heard was, in fact, the highly magnified sound of the workstations.
Rick?
Hi, David. I have a question that I think I know the answer, but I'd like you give your perspective on this. So, because I think it pertains to many of the people that have been that are attending this course. So imagine that I'm a young PhD student in theoretical physics, right? And I come up with some beautiful effects that might be found in LIGO or Virgo data, and therefore my advisor say, well, hey, you have open data and you can basically search the data, so the question would be, so you've been presenting lots of defects in the data, lots of how complicated they are. Is this okay for a PhD student with probably little expertise in the instrument and in those data to start looking at and infer something from the data? That's probably a complicated question, but I'd like your expertise. I'm sorry if I put you.
Good. I'm not so sure that I heard the question therein. You provided a scenario there. So let me talk a little bit about the access of the data, which I think will help answer the question. We'll see. LIGO, Virgo, Cagra all have sharing within their collaborations of the data as it comes out of the machine, but they're not shared with the public until they're well understood and until the initial suite of detections has been undertaken. Students who join a group in one of those collaborations, in general, immediately have access to the private data, of course, with the understanding that they're not to share it outside of those collaborations, and can immediately start to see those data as they come out. Those data, of course, are extremely rich. There's the strain as a function of time, but I think that that is something like 1% of the data that are collected by the various different instruments. And the rest of those data are these auxiliary channels, which are used either to form the full strain channel or to be able to look for data defects. And starting students often start out not so much by analyzing for gravitational wave signals, but instead looking for one of these cross couplings between an auxiliary channel and the gravitational wave data as a way of starting to familiarize themselves with the software tools, with the kinds of things which are significant in the gravitational wave data, to make some friends and do some networking, and to generally become appropriately skeptical of the gravitational wave data, because most of the things that come out of the instrument that look like they could be exciting events just next door in a solar system are just noise in the system. And so that process of initial study is a very important one for many people who are starting in the field before then launching into a process of joining in one of the efforts to identify a signal, estimate its parameters, and then join in the writing of an article. Now, I don't know, Eric, if I touched at all on the thing you called your question. Did I?
No, I think you did. I think the question was, do I need to have a deep understanding of the instrument in order to infer from the data, right? Do I need to have, you know, your level of knowledge of what's going on in there to actually draw some scientific conclusion?
Yeah, I would put it this way. There must be enough people who have that deep level of understanding so that we can ensure that the data are credible. Not every person needs to make that the focus of their career, but we do need a certain fraction of people who spend their time at the observatories and become intimately familiar with the detector. But then I do think that every single person who's analyzing data should get close enough to the detector at some point early in their career so that they do develop this healthy skepticism and develop some intuition for what to believe and what not to believe in the data. That's my belief, at least.
Okay, I don't see any more questions, so maybe we can have a break. It's 4:58 here. What would you like to? When would you like to start?
Let's meet at 5 after. Sound okay?
Yeah, now it's 5 basically.
Yeah, that's right. So let us wait 5 minutes. Okay.
Okay, 5 after. Okay, very good. Okay.
I'll see you in a moment.
See you soon.
Check that my video and screen can be seen.
Yeah.
Great. I can start up whenever you think it's wise.
Well, let's wait 30 seconds, but I think everybody's here.
Okay.
So I think you can start.
Okay, good. So now I'd like to turn to a bit of discussion of the future and then some other instruments. Let's see, first let me looks like I'm going in the wrong direction here. Let me try and get a pointer that I like. And then try to move forward. Okay, good, here we are. So first off, this is a timeline of the observations that the network has undertaken and intends to undertake. We had the 01 observation, which is when LIGO had the opportunity to make a first detection. 02, when Virgo joined and we saw that marvelous binary neutron star. 03 wrapped up, was cut a month short because of the complexities of operating during a pandemic, but led to a very rich collection of observations, which have now reaching publication. We are, between each one of these runs, we take the machines down, install new parts, and recommission them with the objective of increasing the sensitivity. We're in one of those processes just now between the end of 03 and the beginning of 04, where we expect these kinds of significant jumps in the sensitivity of the instruments. This had been intended to start just in the early months of 2022. It looks like there'll be something on the order of a 6-month delay, whether that can be reduced or if it might not increase. Depends upon principally the pandemic. It's also just hard to maintain a schedule to get all the equipment together and so forth. But this gives you an overall map. We intend to continue on making improvements to the instruments and interleaving those with measurements. What does the network look like now and tomorrow? We have these 2 LIGO detectors that I keep talking about. The Advanced Virgo detector. There's a detector actually in Germany, the GEO detector, which is used principally for developing new ideas and has at times observed. It's now watching for a supernova should one come along. CAGRA has just recently joined the team in terms of being ready to collect data, is working hard on commissioning a rather complex and ambitious instrument, but which is really pathfinding for the whole field for future techniques. LIGO India, when we built advanced LIGO's 2 detectors, we actually built a 3rd detector and put it in storage. And India has signed up to build an infrastructure which will receive that detector, and probably a bit later than 2025, but that one will come on. And the objective is to have at least these 3 LIGO detectors sort of keeping pace for upgrades, and along with Virgo and CAGRA, forming a rich and broad network spread over the surface of the Earth. This might address the question that came by earlier on for some position accuracy. In the run that we just completed with 3 detectors, we had roughly 1 signal per week, and about 20% of the sky could fit into 20 square degree error boxes on the sky. That's kind of these spots here. And the pattern on the surface of this Earth is just determined by where those 3 detectors happen to be and where long baselines exist to make precise measurements. There are places where we have extremely poor localization with those 3 detectors, up into the hundreds of square degrees. And there are places where there's actually very good resolution. And GW 170817 happened to be in a place where we had good resolution. That was a miraculous, wonderful set of chances that came along with that detection. When we increase the number of detectors and the openness of the surface that's described by the perimeter from those detectors, effectively the bigger the triangles are that define the distances that you can measure, the more precision you have in the sky. And by the time we get to 2024 is probably optimistic now, let's make it 2025, 26, something like that. There is some 60% of the sky in 10 square degree uncertainty boxes. This is the kind of precision that we'll be able to deliver by mid-century. All of these, of course, are for some system of some signal to noise ratio, et cetera. But it gives you a sense of the evolution of the detection capabilities and the scale of our pointing precision. I want to note that sensitivity improvements are very well rewarded. We have, for instance, an upgrade of the system called LIGO A+, which is underway and will be sort of halfway implemented in 04 and completed for 05. There are similar changes that are underway in Virgo. And the kind of difference in the spectrum that we're talking about here is moving from, well, this is what the 02 sensitivity was. This is what we would expect from the advanced LIGO detectors if they were brought to their full initial design sensitivity. This A+ upgrade makes changes to the quantum sensing, to the thermal noise, to the quantum sensing, to make an overall improvement in the sensitivity of about a factor of 2 or so. That change of 2 in the sensitivity introduces an 8 times greater volume, which is within reach of the instrument, 8 times as many potential sources, 8 times higher rate. It would bring us to the point where we were seeing probably on the order of 100 binary black holes in a month, like 3 per day or something like that. Binary neutron stars, based on our rather uncertain statistics, would become much more frequent, of course, and then other things as well. There's also an increase in the signal to noise ratio for a source at a given distance of a factor of 2, which would be very welcome for doing more detailed studies of things like the Hubble constant, higher signal to noise ratio for tests of general relativity and the like. This gives you a pictorial demonstration of what we're talking about. In 01, that's going from 0 to 1 detection right there. In 02, we started to really pick up more detections with the addition of Virgo and the improvement in the overall sensitivity. In the 03 run that was just completed, there was a solid accumulation of signals over the period of the run, which was quite impressive. This is simulated data for the kind of improvement that we expect from the network in 04. And it's a very rewarding thing. And in fact, it makes it a bit of a tension, right? We can observe for a longer period of time, which increases the sources linearly with the observation time. If we can make an improvement of the sensitivity, we get a nonlinear increase in the number of events, but you're also missing out on observations. So there's some tension in making that trade.
Sorry, David, there was a question concerning the slide before this one, about what are the red crosses. Is it, maybe it's the one before, red crosses in the last slide. Yes, that one.
Yes, those are blind spots for the network. Places where they, we fall at such a low level of sensitivity for the entire system that we can't say where signals are in a practical sense.
Okay, thanks.
Good, so what do we do next in terms of instrument development? One of my early slides had the headline that we couldn't really write down a set of requirements based on the science we wanted to do for ground-based detectors, but instead just had to do the very best we possibly could and tell you what the specifications were for that and see what we could see. Now we can start to envision this transition where we can actually lay out requirements for the systems. This is a slide I borrowed from others, of course. Just to give you a notion, it's very exciting to know what's going on inside binary, inside neutron stars, because it's such an exotic state of nuclear matter. And by looking carefully at the signature at the end of the in-spiral, I think you'll recall that line, which was a nice smooth curve during the in-spiral and then became this terrible noisy jaggle. That tells you a lot, or that tells nuclear scientists a lot about what's going on, what the nature of the nuclear matter is in a neutron star. And this is just a set of different models of what could be there and the different evolutionary states. These kinds of progressions are written in the detailed time signature of the strain as a function of time. So you really want to see that. So now what we can see is, well, let's see if we can find a instrumental configuration that gives us sensitivity in that critical frequency domain of 2 kilohertz to 4 kilohertz. And as an example, there's a group active collaboration in Australia, which is looking at how you would build such an instrument. This is a model that they ran the binary neutron star comes in and then has these very complicated signatures in the post-merger phase. The advanced LIGO sensitivity looks something like this. This team believes that they could tune up on a modest length instrument, but with a very stressful design for the optical components, something which could have this blue curve as the sensitivity, revealing the details of this coalescence epoch. And so that would be an exciting detector to build. It'd be sort of expensive, but now we know that there's science there. We know that if we specify an instrument sensitive in that region, it will see something really exciting. There are more general purpose instruments that are in the preparation and proposal phases. One of them is this next generation observatory, the Einstein telescope. The graphics that this team come up with are absolutely wonderful. This shows this system which is sitting underground under some place in Europe. I'll talk more about its particular configuration. The scale here is really incredible. I don't know how tall these isolator vacuum chambers are, but they're probably 5-7 meters, something like that. There's also a concept that's being developed in the US, which is more likely to be on the surface of the Earth. And as you can see in this illustration, it's expected to have very long arms. This one we are naming a cosmic explorer. Let's look at each one of those in just a little bit more detail. The arms grow from the 3 to 4 kilometers that are currently being used to about 10 kilometers. But the philosophy here is more to stretch the technologies to overcome the test mass motions than to use brute force in length as the tool to get at those. The notion is to put it underground. I talked earlier on about how that reduces the seismic noise, but also critically the Newtonian noise. And because this detector wants to target very low frequencies compared with what we're currently looking at down in the, say, 5 to 10 hertz or even 3 hertz region, this is an important part of it. It also helps with finding a site in Europe. In the US, there are lots of unused deserts. That's not really so much the case in Europe. The concept is to make a triangle out of 3 detectors. Someone asked a question yesterday about how important it was to have exactly orthogonal arms. It's not at all important. And here, 60-degree arms are being used. It allows you to resolve, because there are multiple interferometers installed in this complicated system, it allows a single site to resolve gravitational wave polarizations, probably with very high precision compared with what you can get by having widely spatially separated ones. You can also do things like take sums and differences around the system to get what we call a null stream, a signal output which should carry no gravitational waves, which can be useful in understanding the noise. There are also high and low frequency detectors. There's a red detector, there is a red low frequency detector and a red high frequency detector, which operate in parallel down the beam tubes. And different technology trades are made, for instance, to minimize the temperature of the low frequency detector to reduce its thermal noise. It's also operated at low power so that the quantum back reaction is minimized. The high frequency detector is operated at the highest optical power as possible, and the low frequency sensitivity is thrown away. So it attempts to cover a very broad measurement space with what I personally think is a complicated system. It would be wonderful to see this whole thing built and operating. The Cosmic Explorer US-based approach works on a different notion. The philosophy is to stretch the arms to increase the sensitivity and start with known technologies. The signal size, as we know, is proportional to this delta L induced by a passing gravitational wave of magnitude h, and that grows with length, but not most of the noise sources. Thermal noise, radiation pressure, seismic noise, Newtonian background are all physical motions of the test mass, and they don't grow bigger if you make the arms 10 times longer. So it improves its signal to noise ratio pretty much linearly with the length. In fact, there are even some noise sources that improve faster than linearly with the length. The concept offers sensitivity without new significant measurement challenges. You start at room temperature, start with modest laser power, start with the squeezing we can achieve today. Clearly, the system, the observatory, which in both of these cases, Cosmic Explorer and Einstein Telescope, are designed to last for decades and decades and intended to house a full progression of the sensitivity of instruments. Well, Cosmic Explorer would also install more challenging technologies as they went along, but it starts out as simple as possible. The baseline, which is just starting to firm up actually through a study that's going on in the US, is now to think of proposing for two instruments, a 40-kilometer system and a 20-kilometer system. It remains to be seen whether or not the funding agencies think that that's a feasible concept, but it's the one that we think responds to this notion of moving to requirements for the detector. We have a 40-kilometer detector, which is maximizing its reach to do the deepest cosmology and see to the edge of the universe. And the 20-kilometer arms are focused on getting a maximum sensitivity with a minimum technology stress to look at the final in-spiral of neutron stars. Curiously, in the US, it's not hard to find sites that will house a 40-kilometer detector. The Sagitta is now 31 meters. You'd have to do an awful lot of Earth moving to make that out of a simple curved section of the Earth. It turns out there are lots of places which we typically call bowls, but which are actually geometrically flat areas in the US, also in Australia, by the way, and it would be wonderful to have one of these detectors located there. And that can reduce the cost of the civil construction. There's also a lot of work going on. Ray Weiss, Nobel Prize winner, is spending most of his time these days thinking about new ways to make steel tubes. Amazing man. At any rate, this team is working very hard on reducing the cost of the vacuum system because that's going to be really dominant in the 40-kilometer long system. And this sketch is kind of fun. The initial, the 4-kilometer LIGO facility is sketched here. Einstein Telescope, which makes, as I said, this philosophy of using good technologies in the triangular situation to get good sensitivities. The Cosmic Explorer is sort of a brute force approach.
There is a question on how are the null streams obtained?
Say once again, please.
How are the null streams obtained? It's probably about the previous.
Ah, right. I can't give you the detailed formula, but you can see that you get, in each pair of arms, you get a sum and a difference from a given passing gravitational wave. And there's a complement in this one here, which gets the opposite sign for one and the same sign for the other. And if you work your way around, there are sums and differences that lead to a null stream. I'm sorry, I can't answer that question properly. I don't know if Neil would be able to, but I'll pass that along to him as well. If there were any LISA experts online, they would be able to answer that question properly too. Because it's done also in LISA.
If I may, a simple case where you can compute a trivial null stream would be collocated interferometers. So you have two interferometers in the same site. And by taking the difference between the two, you just nullify the gravitational wave signal. And I mean, you explained this very well. If you're not in this case, you still have a linear instrument. Therefore, there is some linear transformation of your data that nullifies the gravitational wave signal.
Thank you. Yes, that's a good example. And in fact, LIGO started out with 2 and 4 kilometer long arms at Hanford. And we tried actually forming the null stream, but we found it too hard to commission 2 interferometers. It's just too much work. And so we never really got out of that what we could have. But no, that was a very good explanation. Thank you.
Another question is the cost, the order of magnitude of the cost of a Cosmic Explorer.
The current guesses are coming in for a 2-instrument configuration of a little bit more than 1 billion, that is to say 10 to the $9. And I think, I won't give numbers for Einstein Telescope. If anybody wants to say them, they're welcome to. It remains to be seen, as I said, whether or not the funding agencies are in any position to realize these detectors, and whether or not they will be able to realize our full vision of what would be best in the case of Cosmic Explorer, or if ambitions for a 2-detector system will have to wait for another few more decades. We'll see.
Thank you.
Okay, here is a notion of what the sensitivity of these detectors look like. Here's advanced LIGO, usual strain on a logarithmic scale, frequency on a logarithmic scale, still these rough audio frequencies. Advanced LIGO is up here. That high frequency detector the Australians are studying would look something like this. We hope to get to this sort of sensitivity curve around 2025 in LIGO. There have been some proposals for some things that one could do in the 4-kilometer baseline by tearing out most of the current detector and replacing it by, say, a low temperature detector in LIGO that could make some incremental improvements. But to make the really big jump down to the sensitivities associated with Cosmic Explorer and Einstein telescope, you need to build new observatories with longer arms. And there's some details in the sensitivity curves that depend upon the science foci of each one of the 2 detector projects. This is a different way of looking at the reach of those detectors. I'm getting dangerously into astrophysics at this point. I'll stop soon, I promise. But here's a plot which has got a different set of axes. This is the redshift, how far one can see into the past and into the distance. And then here is the mass of a binary system being detected in its frame mass. Once the redshift is significant, that can differ a lot from the mass that we observe here. The initial detectors that are currently operating look something like this in terms of their reach. They have a best sensitivity above 100 solar masses and can reach a bit above redshift of 1. The best that you could do in these 3 and 4 kilometer systems that we can currently imagine would bring us up to a redshift of a few and bring us down in the target mass a bit. Einstein telescope and Cosmic Explorer can reach beyond the point to which we think there are any systems. They can see all of the coalescing binaries in this frequency range of kind of tens of solar masses in the universe. And that would be a wonderful thing to have as a population study. Okay, when could this new wave of when could this new wave of ground instruments come into play? It looks like it takes about 15 years, at least in the past, to build these things. It might take less time. I don't think we have to scale up the time of construction by the length of the instruments or their complexity or their cost. So I think something like 15 years makes sense. And so you could imagine somewhere in the 2030s. We should see that it would be wonderful to have these instruments running at the time that the LISA project, I'll talk about that in a couple slides, when that's going as a way of doing joint measurements. There is a broad community working together on concepts and the best observatory configurations for the science targets and trying to knit together the activities in Cosmic Explorer and Einstein telescope. The Gravitational Wave International Committee, you can find the link here, is a collection of all of the members, all of the projects that are working in the gravitational wave field who try to do some level of coordination. Crucial for all of these endeavors is to expand the scientific community, which is planning on exploiting these instruments. You need to find that there are thousands and thousands and thousands of scientists who think that the data from these instruments will be the thing that realize their scientific objectives. The costs are like one of these big ground telescopes, and you need a comparable audience to motivate those kinds of expenditures. You need to find people, in particular, you need to find traditional astronomers who are willing to say, who are willing to argue to the funding agencies that instead of building another 30 or 40 or 50 meter telescope on the Earth, that it would be a better thing to build a gravitational wave detector. And that requires quite a shift in perspective, which is underway with events like GW170817, where traditional astronomers find that the qualitative addition of a new kind of messenger allows them to do things that they couldn't do with a bigger telescope. It's a transformation, and people like you are going to have to play a role in deciding that you like this idea and arguing that it's part of your scientific future. So let's go back to this big map of the various different domains in frequency and the techniques used to observe them. I want to spend a bit of time talking about pulsar timing, which is looking at these frequencies of inspirals on the order of 10⁻⁹ Hertz. we use pulsars, or those folks who are pursuing this approach use pulsars, spinning neutron stars, as their test masses. These are objects scattered through space. Neutron stars tend to spin because of the accretion phenomenon that forms them. They tend to have magnetic fields for the same reasons. And a remarkable number of them, although they have a beamed electromagnetic emission, that beam happens to be aligned so that it sweeps across the Earth. These extremely stable clocks allow us to look for shifts in the arrival time of the ticks from those clocks, and to interpret shifts in those times due to a differing optical path, due to a deformation of space-time from a passing gravitational wave. Looking at any individual neutron star wouldn't give us any high signal to noise ratio measurement of that. By looking at a collection of the pulsars scattered around in space, you can imagine that there is a unique signature of a passing gravitational wave. If we had simply a plain wave passing like this across this illustration, you can see that the distances to these pulsars should be shrinking at the same time they're expanding to these pulsars, and then the converse at another half phase. That's the kind of signal that these folks try to extract from a whole field of pulsars. Because of these very long baselines, the kinds of gravitational wave wavelengths lead to looking at very, very massive systems, which are in spiraling supermassive black holes at the centers of galaxies, two galaxies spinning around each other extremely slowly. This leads to a point sensitivity, which is best around 10 to the 7 to 10 to the 10 solar masses. Also, because of the time duration of an in-spiral, turns out that the best candidate, initial candidate at least, is a stochastic background, an astrophysical one. It's not thought at this time that there will be a primordial background at a level which would be detectable, but an astrophysical one due to all the galaxies in the universe spinning together, yes. And from that stochastic background, its color and its amplitude, important conclusions can be made about the formation of these supermassive black hole systems. These folks now have some indication of a signal, some excess of noise in a certain frequency range, which would be symptomatic of a signal. They don't yet have a good enough signal to noise ratio to say that it has the signature of a gravitational wave, that differential stretching and squeezing of space-time, but they continue to observe. So as I said, the test mass is offered by the pulsar and its rotation. A radio telescope catches many low signal to noise ratio blips as this thing spins around at some frequency from tens of hertz up to kilohertz. There's a de-dispersion process. The interstellar medium has, of course, molecules in it, and just like along our vacuum pipe, that leads to fluctuations in the apparent distance due to that. But more importantly, as a function of frequency, the optical length changes, and that needs to be removed as a de-dispersion. Blips are folded on top of each other to increase the signal to noise ratio, and then a fit of signals to multiple pulsars is made to create a measurement of whether or not there are gravitational waves passing. Here's a photo of some of the instruments that are used to receive those signals. I'll call your attention to one of them, the Arecibo Observatory. I imagine many of you followed its recent demise through the collapse of the cable system, which was holding up this receiver, and the subsequent collapse of other parts of it. It does not look likely that it will be reconstructed. It may yet be. There may be better ways with a similar investment to build a different radio telescope that could take up once again the job of searching for gravitational waves along with all the other things you can do with radio telescopes. And of course, the other important ingredient to the International Pulsar Timing endeavor is the people. I found a nice photograph of the team here. It's spread around the world. It requires allocation time on instruments worldwide, and a lot of work in bringing data sets into common formats and doing the number crunching. It requires a lot of understanding of the detailed behavior of pulsars. Pulsars have personalities. They show glitches and so forth. Finding additional pulsars also improves the sensitivity, so that's a search. And then ultimately, when all things are working well, more sensitive detectors, more pulsars, it could be that some individual sources can be observed. But at least initially, the objective is to see the stochastic background. Okay, and for our last chapter here, I want to talk a bit about space-based interferometers, which are measuring in this intermediate frequency range of something like 10 to the minus 4 hertz, and looking for massive, but not super, super, super massive black hole mergers, among other things. LISA, the Laser Interferometer Space Antenna, is a project that's very far along and with which I'm fairly familiar. There are some other projects in particular in China which are moving along, but I don't know so much about them, so I'll just talk about LISA. The arms lengths which are chosen for LISA are 2.5 million kilometers. Clearly, this is much, much longer than the around 2.5 kilometers that we use on the ground. We have a limit to how long we can make the arms on the Earth for a couple of reasons, but among them is the cost of the vacuum system. Once you get objects up into space and working, well, you might as well separate them a long distance. You don't have to pay more for the vacuum between the two, between the objects. It moves the best sensitivity because of the match to the wavelength of the gravitational waves to more like, say, 1/100th of a hertz or so. And the target masses from the sort of 10 to the 2 solar masses of the ground systems up to 10 to the 6. And also in contrast to the pulsar timing of 10 to the 9 or so. The way they form test masses, we'll see this in a bit more detail on following pages, is to have a cube of very pure material and put a box around it, measure the distance between that cube and the box, and servo the satellite, which holds onto this box, to follow the test mass around, protected against solar wind and so forth. The orbit scans the sky so that you can, over the period of a year, observe things from a number of different angles and also from 2 different positions separated by 2 AU. And it uses interferometry, optical interferometry, to sense the path lengths, although in a rather different way than from LIGO and so forth. I have a nice short illustration here of the intended orbit. The separation of the masses is actually exaggerated here, but it gives you a notion of the stable, fairly stable orbit that is intended for LISA. The measurement concept, test mass to test mass, the distance is measured. Well, here is a test mass. It's a 2 kilogram cubed of platinum gold. Interferometry is performed between a surface of this little test mass and a reference table, and then between the reference table and a telescope, which couples the light over to the next satellite 2.5 million kilometers away. And so that distance can be measured with some interferometric precision. It's interesting to note that about 2 watts are broadcast from one of these satellites, and some 10 to the minus 10 watts are received due to the diffraction spreading of the beam. A larger telescope would make less spread. Larger telescopes are more expensive to launch. This is a trade for practicality. There are also 6 independent lengths which are measured between each one of the satellites and in each direction. Those 6 links are combined on the ground in a way that allows you to resolve out the gravitational wave signal and to suppress some technical noise and to form that null stream that was discussed before, also using time delay interferometry, which is basically, initially it starts out as just a bunch of algebra to calculate when signals would have been seen from each one of these paths and subtract the right time offsets to reconstruct the strain that happened at a given moment. It gets more exotic once you take some more 2nd order and 3rd order effects into account.
I think there is a question, Luis.
I'm not sure I'll be able to answer it. Go ahead.
Hello, can you hear me?
Yes, I can, thank you.
I'm not from the part of instrumentation. It seems to me that it's a way long arm length to use lasers. We have this technology and the quality of lasers here on ground that can give this a laser coherent to this distance, or is it still some developed to go?
I'm not sure I understand. The distance for the laser is, when it presents a couple of practical technical problems. We're forming a very asymmetric interferometer with an arm which is a couple centimeters and an arm which is 2.5 million kilometers, which means that there are laser frequency noise issues. Those can be resolved by this time delay interferometer of taking sums and differences. The laser is actually a really nice way to do satellite to satellite communication. The beam from a laser spreads out much, much less than a radio wave, and you can more easily get more energy into the coherent beam of the laser. So it's actually a pretty nice way to do this communications process. And there are, I think it's mostly for military satellites, but there's actually a fair amount of practice in using lasers to do inter-satellite communication. So it's a good way to go. It delivers the signal to noise ratio that's needed and uses technologies which are familiar to many of those in the field. I hope that addressed the question.
Yes, it does. Thank you.
Okay, good, good. Looking a little bit more carefully at the sensing assembly, let's see, I should move along a little bit here. There's a 30 centimeter telescope. I can tell a story here. The US is supplying the telescope. And as its contribution to the actually ESA-led, European-led consortium. And there are a bunch of export laws from the military and from any given country about what you can share with other countries, even between friendly countries. It turns out that it's extremely hard to share a telescope larger than 30 centimeters with any country other than your own. You can guess for yourself why it is. Or I can tell you that it's because people use larger telescopes than that to look from satellites down at the Earth. At any rate, this is a 30 centimeter telescope. It also turns out to be big enough and also not lead to too much weight in the satellite. And that's coupled after it's an off-axis telescope that couples the light down to this optical bench, which is just full of optical components to form the interferometry between the incoming light beam and the test mass, which is housed behind in this vacuum can. There are two of these units, of course, which are assembled into each one of the corner stations of the LISA configuration. Because the orbit is not perfectly stable, those two actually have to change their angle slightly to track. There was a LISA Pathfinder experiment, which involved sending up into space a satellite, which consisted of two test masses in their cages and one optical table to compare the distance between those two cages. It was designed to demonstrate that one could make this sort of interferometry work, and most importantly, that you could actually make a caged mass, which would be free of external forces at the level required for LISA. It worked beautifully. It worked better than its specifications. It worked better than the ultimate LISA requirements, giving us and funding agencies confidence that we can master this very, very challenging part of the experiment. It was said, and I don't have any reason to argue with it, that these cubes, while this experiment was operating, were the quietest places in the universe. If you actually had this cube just sitting out in free space, it would be buffeted by solar winds, particles, and so forth and so on, micrometeorites. In here, it's protected. Everything else is outside. Let's see, so sensors measure the distance from the test mass to the cage, and then low force thrusters push on the spacecraft to keep the cage equidistant from the mass at all times. The initial balancing is critical. The gravitational attraction, I use that term loosely, of course, it's really the warpage of space-time, but the gravitational attraction of a test mass, say to a paper clip sitting out here somewhere, would be fatal. The mass would feel an attraction to that paper clip and head in this direction, which would cause the satellite to do the same. So very careful balancing is required. I was looking for a good place to summarize the sensitivities of ground-based instruments in LISA, and I found a presentation I made, I don't know if I should be pleased or embarrassed, in 1998, which is still pretty much up to date. Ground-based instruments observe in these audio frequencies. LISA observes in sort of a complement of frequencies below 1 Hertz. The sensitivity to one cycle of a target system for the ground-based systems is about 10 to the minus 23 strain per root, integrated strain. That same number is true actually for LISA, but at a very different frequency and a much longer integration time. Arm lengths are sort of kilometers or sort of billions of kilometers, 10 to the 9. Displacement sensitivity needs to be far better on the ground than for LISA. LISA is taking advantage of its very long arm length to boost the delta L up and to allow a simpler interferometric system to be used. The stochastic forces that we deal with on ground-based systems are addressed by seismic isolation, very fancy suspensions, which exhibit very low thermal noise. In the case of LISA, we use this inertial sensing trick to protect the test mass from some external forces, use servo control systems to make this drag-free technology function, and then watch very carefully the thermal balance in the spacecraft, because if one side of the spacecraft gets a couple of degrees C warmer, it will expand away from the test mass and look like a gravitational wave. The sensing systems uses lasers in both cases. Here we improve ours by making better and better, higher and higher laser power and making more and more fancy optical development. And in the case of LISA, we use very careful clocks and corrections to laser frequency noise by taking sums and differences around the configuration, and use this transponding system to relay information from satellite to satellite. What does this LISA sensitivity curve look like? Again, stray forces dominate at low frequencies. Just like they do in LIGO, the stray forces happen to come from mostly different things. There's some common things like electrostatic forces. Then at the mid-frequency region is dominated by the shot noise, the quantum noise. These are, of course, the radiation pressure from 10 to the minus 10 watts is negligible. This sensing technique is completely immune to the radiation pressure domain, and however, is very susceptible to the shot noise domain. And so that sensing noise dominates here. And here we see some wiggles in the response, which happens each time another wavelength of gravitational wave fits into the arm lengths of the detector. I'm not going to talk much about this, but this shows now, this is another example of an instrument where it's really designed for the science. And this gives you some idea of what those science goals are. These curves indicate the trajectory in frequency of some systems, for instance, a 10 to the 5 solar mass binary in spiral. You'd start to observe it about a year before it was going to coalesce. And for instance, if you thought that there might be something that would be of interest to either ground-based detectors or to electromagnetic observers, you could tell them, say a month in advance, well, you might look in that part of the sky at this particular moment, because that's when we think the coalescence will take place. And in particular, there's a group of lower mass systems, that's 10 solar mass, 100 solar mass, 300 solar mass systems, which coalesce starting in a frequency range which is visible to LISA, and then wandering over a period of months or a year to the frequency domain, which can be seen by the ground-based detectors. And those could provide there's some nice terminology for the measurements which take a multi-band measurements of gravitational wave gravitational wave systems, which could, for instance, allow much more stringent tests of general relativity. There's also a lot of gravitational noise, right? This system, when you turn it on, is expected to just see thousands and thousands of signals all superposed on top of each other. There will be some which will be very, very loud and relatively easy to extract from that data stream. But a lot of the ones which are of interest will need to be simultaneously fit out of the data stream, which is going to be quite a computational challenge. And well, certainly I can tell you there's a great deal of activity on the ground in LISA now to design the physical sensing system, because deadlines are approaching for actually locking down what those are going to look like for a launch in 2035 or so. But there's also a feverish activity to figure out how to do the data analysis and extract all of the data, all of the science that will be available in the data if we have the means to do it. Okay, we've wandered through the full slide deck. The things I want you to carry away from this: the instrumentation touches fundamental physics in many domains. There's surely a great deal of, I would maybe call it ordinary engineering. There's a lot of exceptional engineering. There's a lot of simple complication. There's a lot of dealing with defects and shortcomings of what we built. But all along the way, there's constant contact with fundamental physics, quantum physics, thermal physics, material science, evidently touching ultimately on general relativity and so forth. That makes it a fascinating field, and one which is really multidimensional. The systems to make detection are complex and rich. You can focus on any one of a number of precision measurement concepts and discover that you're really pushing this art forward. The source domains are mostly or entirely unexplored. We have seen binary inspirals of black holes in a certain range of masses with a certain range of spins. We've seen a couple of neutron star inspirals, some of which have been able to be seen also by electromagnetic sources. There are lots of other sources that we're sure are there, and lots of other examples of current sources which will bring new science. A wonderful thing from my perspective and in the long term is that all the detector domains have clear paths to refinement, improvement, and extensions. Some of them require some real innovation in precision measurement. Again, fascinating work in and of itself. A lot of them require very significant investments by funding agencies and very significant investments by large numbers of people in a coherent, synergistic way. But I think it's feasible to think of this field as being one that will continue to grow and can be an exciting place to work. It's also just a really interesting environment from a social and career perspective. I do think that there will be further evolution in the balance of competition to cooperation to collaboration. The collaborations will certainly continue to evolve in terms of their structures, and may have to develop even more rules if they get that much bigger and require that much more structure to reward people and ensure that all are contributing fairly. But I think it's going to remain an interesting place to work, and one that I think it's really worth study and communication with young persons who are currently involved deeply in the field to find out if it might be a good fit for some of the persons who have attended these lectures. And so with that, I will draw to a close. I have a last slide, which is just full of pretty pictures. Thank you.
Thank you very much, David, for these beautiful lectures. So we can take questions. There is one, maybe Luis, you can spell it.
It was meant as just a small comment. I once went to a lecture and the professor said that you can work within the gravitational wave community without even talk about gravitational waves, in the sense that there is so much physics in the instrumentation part that you can work in several realms of physics. So it was just a cool comment that I...
Yes, and a germane one for me. I started out in this field in the late 70s, and with absolutely no knowledge or interest in astrophysics or general relativity. I liked building cool stuff. And I've found a mentor, same person, Ray Weiss, who wanted some stuff built. And so he hired me. And the first 3 or 4 decades that I worked in the field, I had only the most passing understanding or really deep interest in the astrophysics, but I got more and more engaged in the fundamental physics of the measurement system, and also in the meta activity of coordinating people and trying to design full systems. Now that we're making detections, I'm turning into an astrophysicist, and it's wonderful to be able to develop a new field expertise while staying in the same experiment. But I think it's really true. You could be a quantum measurement physicist and discover that these instruments are, for instance, the only way that you can make measurements of the quantum state of a 40 kilogram object. It's a unique measurement device for that kind of physics. So you're perfectly right on target to make this observation. Thank you.
Okay, so there is another question. When do you think we'll be able to see, 1, the post-merger signal of binary neutron stars, 2, gravitational waves from supernova, and 3, continuous waves from pulsars?
Okay, so let me first effectively restate what I just did. I'm an instrument builder, but I know a little bit about the astrophysics, and I'll tell you what my impressions are. You might want to ask some of your other presenters and see if you get the same answer to do triangulation. For the, when will we see the, let's see, I think I can remember these. When will we see the first binary neutron star coalescence signature? We will have in our next runs starting in around 2022, instruments which are another factor of 2 more sensitive. And if we were to see a replay of our one spectacular event, GW170817, with those instruments, we would be able to say far, far more about the equation of state of the neutron stars. It wouldn't be a pristine high signal to noise ratio measurement, but it would already be a situation where you could say much, much more. The next question was about supernovae. When will we be able to see them? This is a bit of a sad story from my perspective. All the models for gravitational wave emission from supernovae at this point indicate that a very small amount of the energy of the explosion is converted into gravitational waves. And the reach of our instruments to the amplitude of signals that are currently expected puts it so that we can only see those supernovae which are in the Milky Way galaxy. And those happen on average once every 100 years. Now, I don't think you have to take 1987, add 100 years to it to calculate when the next one will be. Of course, this is a stochastic process. And so there's a chance that we'll be able to see one sooner. But this unfortunately remains true even for the instruments, the Cosmic Explorer and Einstein telescope. They do increase our reach by a factor of 10. There just isn't a lot of stuff, another factor of 10 further away. So then the third question was, what was the third question?
Continuous waves from pulsars.
So the current limits to the size of the bump on a pulsar that we could see in our current observations, I think is down to a fraction of a millimeter of asymmetry over an object which is some 10 kilometers in diameter. Radius, I think, I'm not sure, somewhere around there. At any rate, of that order. So the sensitivity is already exquisite for the searches. It could be that there's already a system out there and we just haven't been able to observe all of the space. Recall that I said that there's a Doppler shift of the signal due to the relative motions of the Earth and the source. And to look in a given position in the sky with the best sensitivity, you have to correct for the Doppler shift in that specific direction. The computational demands are, we do not have enough computers on the Earth, I believe, to be able to do a full sky, full Doppler shifted study of the entire sky at a given time. And so compromises have to be made in our ability to delve into the data which we already have. And it could be that there's something already there, and it could be that it will pop up soon. The other thing to note is that as far as I know, those theorists who are predicting the range of ellipticities of neutron stars, which are feasible given our rather limited understanding of the stiffness of the crust, project that we could still be a couple of orders of magnitude away from having a sufficient sensitivity for seeing the signals from likely deformations on neutron stars. So it's a stretch. It's one which would be fascinating to realize, and it's definitely one of our prime targets and one which influences the way we build our instruments and the way we analyze our data. I won't make any bets for when we will actually see our first signal.
Okay, thanks. Eric?
Yes, David, I had a curiosity about this NEMO project that you mentioned that I'm not aware of. You said that it would be stressful for the optics, so I'm curious about this. So what is the concept of the instrument, and do you say stressful because it would be very high power, I presume?
That's exactly it, yes. The notion is to, well, so the current LIGO Virgo concept is to have something under a kilowatt of circulating light in the arms. And so this NEMO concept says all we're going to do is try to beat down the shot noise and make a measurement at relatively high frequencies where most of the mechanical noise sources, which have this 1/f to the n characteristic, have fallen down to a level which is negligible. So it's all about getting high circulating power to drive down the shot noise limited sensitivity. And the number is something like 10 megawatts that they hope to circulate. So it's not factors of hundreds away from what we currently think we could support. LIGO and Virgo are already having a lot of trouble just with a fraction of a megawatt. And there are torques on the mirror, which are problematic. There's the absorption of light, even 1 part per million absorption. The kind of current coatings would lead to completely deformed mirrors due to the heating of the mirrors. And the cleanliness requirements and the purity of the coatings, all of those things make it challenging from a technical standpoint. But there are a lot of challenges which go away because of the high frequency nature of it. So it's a concept. It's one which could be a retrofit for one of the existing vacuum systems, Kagra, Virgo, any one of the 3 LIGO detectors, say either as an intermediate state before the full scale Cosmic Explorer and Einstein telescope are realized, or as a parallel 3rd detector, an inexpensive detector to get the most out of that region of frequency space. I don't know, well, that's about all I know about it. I think it's one of these things which will turn out to be, even if we choose not to realize exactly the design upon which it's being worked, it will certainly turn out to be a useful way to motivate the exploration of pushing technologies forward that will be useful in the full-scale instruments.
Thank you.
So another question from Luis, maybe I can, is it reasonable to think a next generation detector and using current LIGO facilities and extending the arms?
Good question, no. It so happens that I think it's also true for Virgo, certainly true for Kagra, true for the 2 US LIGO sites, that there are some very serious pieces of landscape in the way. In the case, for instance, of Hanford, there's a huge river, the Columbia River, and then a bunch of mountains on the other side. It would be extraordinarily expensive to try to extend the system for, I think, any of the current observatories. I haven't done a study for Virgo. Of course, Virgo is in a relatively populated part of the world, and it could be that you'd have to tear down some churches and put the end station in the middle of a town somewhere. That doesn't look like it's a very practical approach. There's also some tuning that's being done of the infrastructure, which would make it so that you probably couldn't, without quite considerable expense, modify the given infrastructure and reuse it correctly. So we'll probably just start over again.
There is a river as well close to Virgo that would be intersecting the extended arm.
So another question is, what variables go in as priors to predict the expected numbers of events for 04 and 05?
What we do is to calculate from our observations to date a density of sources per galaxy, and then from our current known distance and event rate and an accounting of the galaxies within reach, or statistical guess at the number, and then just calculate the number of galaxies that are in shells further and further out, understanding that the signal falls as 1/r as you get further and further away. Clearly, for those signals for which we've seen no events yet, we can't say an awful lot, except simply to say, well, the number of candidates is growing as the reach becomes larger, and so the probability of a detection goes up.
Okay, then there is a question from Paul. This is more of a personal question. Sorry for that. Any trivia about the day you learn we detected the first signal?
Well, let's see. It was obviously a moment where when everybody asked themselves immediately, how could this possibly be true? I'll remind you or tell you perhaps for the first time, we had just finished commissioning the advanced LIGO detectors, commissioning, that's to say, brought them to initial sensitivity and reliability, understanding of the noise sources, so that we thought that it would be worthwhile to start an observation run. So we planned it to start on a certain day. A week before that day, we decided to start an engineering run just to see how the instruments were running, get the operators used to operating them. And it was during that engineering run that this first detection was seen. And it was so loud. It was so clear. It could be seen directly in the output of the system if you just put a high pass and a low pass filter on it. And initially, it seemed far too good to be true. And the fact, though, that it appeared in two widely separated detectors with a very similar signature was an extremely powerful argument that it was a real one. Interestingly, one of the things that people first suspected was that it was a signal injection. We have the capability, using the photon calibrator or other actuators on the masses, to play back a synthesized in spiral force versus time, strain versus time curve. And we did that frequently in the early days as a way of testing, well, first off, whether or not the systems were functioning correctly, whether or not the systems for extracting the signals from the data stream could actually follow through from real data, to check whether or not we had the sign conventions right between the two LIGO detectors, play the same thing back in the two of them, so forth and so on. And we were just in those weeks before the start of the run, exercising the injection system and trying to make it work correctly with the new LIGO configuration. This is the first time we'd run advanced LIGO. I was in charge of the subgroup that was trying to make those injectors work. And we'd been struggling to succeed in making successful simultaneous injections, but we failed for reason after reason, not very interesting ones. So I knew immediately that it couldn't be an injection, but very many people in the collaboration were convinced that it could be nothing but that, because it was such a clean, pristine signal, which made sense. So that it was a joyous moment, clearly. It took, I'll say, there was an immediate, I'll say, intellectual appreciation that it must have been a gravitational wave signal. It took months and months before I integrated it into my worldview that we were post first detection.
Thank you very much.
Any other question? Okay. Oh, Konstantin?
Yes, sorry, I hope you didn't mention it already, but how problematic are, for example, lightning storms or local charges in your environment?
Good question. In fact, there's fake news. And it's a very valuable thing to do. There are a number of people in the scientific community who have doubted, especially our first detection, but then all of our detections following, there's always somebody who's got an alternative idea for what the detection might be. And that's science. It's good to do those kinds of pursuits and ask those kinds of questions. Clearly, it's also important that those people who raise objections need to be ready to accept that their proposal was not actually the right one, but never mind. For one of our first detections, it so happened that there was a lightning strike in the US, which was, sort of mid-spaced between the two detectors, so that you could imagine the electromagnetic pulse from that lightning strike propagating to the two detectors and being quasi-simultaneous, as was the observation of the two gravitational waves. It's 10 milliseconds, by the way, from one LIGO site to the other. So any real gravitational wave must occur within that time window. So at any rate, as it did for that one. So the immediate question was, well, wasn't it just the lightning strike that caused an electromagnetic field near the test mass and causing a deviation? you may not have noticed that among that long list of detectors that I mentioned, there were RF receivers, and they actually realized I neglected now to include in that list the fact that we also measure the electric field in a broadband way just by using a simple antenna in a number of places. So we have a very clear map of all the electromagnetic pulses and can exclude any times when it looks like that would be a bothersome thing. It is a fact also, though, that those vacuum cans that you saw made of a millimeter thick stainless steel work very well as Faraday cages. And so the amplitude of an electromagnetic pulse is extremely attenuated by that. And so this is one of those cases where it's easy to build a detector which is much more sensitive than the instrument to a possible source of environmental disturbance, and to use it as a way of rejecting data that would take place during that suspect time.
Okay, thanks a lot.
Sure.
Paul?
Yes, another question, David. Yesterday you mentioned that you can actually, well, I don't remember if you mentioned this, so that's why I'm asking. Do the data from the interferometer, when it's not about gravitational waves, which is you know, a lot of the time, can it be used for other physicists to do science with it? Do you actually give this data for, I don't know, seismic physics or anything?
There is some other science that can be done. Specifically seismic physics. Turns out that we are a really, really wasted, useless site for seismic measurements. And it's for a couple of reasons. First off, we do everything we possibly can to make our test masses independent of seismic noise. So with our anti-seismic measurement systems. And then while we do have seismometers, and some of them are actually even buried to reduce some of the environmental noise, what we want to know is what the local environment is. And we are actually our own worst enemies. A lot of the seismic environment, which is bothersome for us and for which we must monitor, come from anthropogenic activity, which is around the site. Cars, trains, people, jackrabbits, so forth and so on. And so all of our instruments are measuring things which are relatively uninteresting to real seismologists. They want a vault which is far from everything and is buried deeply. We actually have some instruments like that we use to help monitor the earthquake activity and separate things that we do from others, but it's just not of the quality that they need. Other science, it's not a timeshare system. We don't invite groups in to do other things with the instruments, clearly, because that supernova could go off at any moment. Our obligation to our funding agencies is to be up and observing gravitational waves just as much of the time as possible. There have been some experiments done, I mentioned peripherally, using the fact that it is the most extreme device in some set of parameters for being able to measure quantum effects. The quantum state of the test masses has been analyzed. There's also been perhaps the first measurement of the back reaction force for a macroscopic object done with the data. And these are usually things which are slipped in during the commissioning period. Measurements made when the instrument isn't really ready for astrophysical measurements, but where a day or a couple of hours can be taken of data, and perhaps also in a configuration which is not optimal for gravitational wave detection, but which is optimal for this alternative precision measurement system. At present, that's something which happens within the LIGO scientific collaboration, even more specifically within the LIGO laboratory, which has got the fiducial responsibility for operating these two observatories, and it's a Caltech and MIT undertaking. And so it's not something which is really it's not an easy thing for everyone to get involved in, but there are other scientific teams doing that. And if you're interested in those kinds of measurements, just take a look at some of the quantum measurements that have been made with LIGO, probably also some interesting ones done with Virgo. I haven't kept track, and look at the team members and get in touch and see if there's something you want to do with them.
Thank you very much.
Any other questions? can you say a word about detection through atomic interferometry? Or even possibly other new techniques?
Good. I think atomic interferometry is a really interesting possibility. It's clear that this approach, which is basically tossing an atom up against against the gravitational field on the Earth, changing its state and watching how it evolves as a way of effectively doing matter wave interferometry, can be a very, very sensitive means of measurement of some fundamental scientific parameters. I think they're already making gravimeters, systems for measuring the exact value of gravity of extraordinary precision, which can be used, say, for prospecting or looking at the change in the distribution of water on the Earth, which is something which is an important matter, say, for looking at the change in the water level near the coasts and so forth and so on. There are also some proposals to use this method to do gravitational wave detection. And I think there's promise there. Certainly, if you make the numbers for systems which you could imagine constructing, the sensitivity in some frequency ranges, and probably best targeting around 1 Hertz or 0.1 Hertz or something like that. And for systems which might best be made off the Earth's surface in satellites, this could be the best way to look for primordial gravitational wave background. My sense is that the technology is at a fairly immature state. I think of it as being kind of in the state that LIGO was before we were quite ready to propose to our funding agencies for hundreds of millions of dollars. It's at a time when we knew interferometry worked. We could write down a set of extrapolations from the measurements that we'd already made. We'd explored along the axis of a couple of those parameters like seismic isolation or shot noise or something like that, and had done a good enough job of that so we could start to talk to funding agencies about the credibility of making systems that would be full scale and would have high sensitivity. And my sense is that the atomic interferometry crowd is about there. Of course, that's where we were in 1980 or something like that. I don't think it's going to take 30 years of development in atomic interferometry to leapfrog to the point where they're ready to build full-scale instruments. Science is going to go faster. Some of our technologies could be used to help solve the problems that they'll have. And so I think it's something that we could think about seriously, for instance, as a follow-on satellite to LISA. But it's definitely something to follow up. And it's another one of these situations where there's great fundamental science being done, which can have also impact on a number of other scientific domains. And that is absolutely everything I know about atom interferometry.
Other questions? Okay, so I just want to remind that all the lectures are, those that are recorded are on the website of the workshop, so you can find them there together with the PDF file of the lectures. So David, there are other thanks in the chat. There are people who would like to thank you for the very nice lectures, very informative and didactic. So thanks a lot.
It was a little bit daunting, a little bit challenging, but in the end, a lot of fun to prepare them. And so I appreciate the invitation, and I'm glad that there were some folks who found it interesting and stimulating. Thanks a lot. And if tomorrow you have time to join the gather room in the afternoon, in our afternoon, in the morning for you, well, you are welcome. I hope to, but I'm not sure. I've got some other things I'd have to work my way around. We'll see. No problem. Okay. Okay, thanks a lot. And let's join again tomorrow at 10. Okay. Thanks. Bye. Bye-bye.
Thank you, David.